Hello everyone. So again, welcome back. Let's continue our discussion regarding the solidification and stabilization and relevant aspects. So we are going to move on to relatively more technical aspects, as in we looked at the relevant aspects, as in what's going to happen to the contaminant during solidification and stabilization, how can it be transported, and so on and so forth, right? And we looked at obviously physical transport and diffuser transport. Physical transport, again we looked at, I believe, hydraulic conductivity 10 power minus 5 to 10 power minus 8 typically, let's say, right? Again depends obviously on the porosity too. Porosity you can estimate from the water to the cement ratio, as in typically is, let's say, water to cement ratio minus 0.1, as in if water to cement ratio is 0.5, then the porosity will typically be around 0.4 now, right? Again, different aspects. And then we started discussion regarding leaching now, right? So what is this about? So let's say I have pore space in my relevant solidified and stabilized mass, and within that pore space I have water, and I have the compound, or your contaminant in that aqueous phase, let's say. And even though there is no advection, as in the water is not flowing through, let's say, but this particular contaminant, let's say if it is not contaminant, this solid, let's say, or your solidified and stabilized mass or block, let's say, is in contact with water or leachate, let's say, right? So let me try to represent that here. So let's say this is my solidified and stabilized block. I'm just drawing that as a block, but need not be. And let's say I am going to have pores within it, right? And within this pores, let's say I am going to have the contaminant dissolved in the water or in the aqueous phase. So even though there is no net flow, let's say advection is when we have net flow and this contaminant is flowing along with this water, let's say, even though there is no such flow, and let's say this mass of your, so there is no flow, but let's say this mass of your solidified and stabilized block, let's say, is in contact with the leachate, let's say you have some leachate here, let's say, assume that this is the leachate and it's in contact with the leachate. So what's going to happen here, or how can the compound be transported? As we discussed, it can be transported by diffusion. Why is that? Because there is no contaminant in this leachate, right? And there is contaminant within the, or the dissolved contaminant within the pore space now, right? So obviously due to diffusion it can, or it will, if there is obviously the leachate here too, and this is the pore space, right? Your compound is going to diffuse out, right? So let us try to see how we can try to understand how much will leach out and so on and so forth. That's something we obviously need to do, right? So again, what's the approach here? It's based on material balance, right? So we are going to look at mass balance or material balance, right? So here let's say do we have any advection term here? No, right? We are assuming that it's the transport is only driven by diffusion now, right? So let's try to write the mass balance equation for that. We know that it's dC by dt is equal to the effective diffusion coefficient or dispersion coefficient, depending upon how we look at that, and the second derivative, let's say, right? And second derivative of concentration and any sources or sinks. So let's say rate of loss due to maybe precipitation or such, let's say, right? Again, keep in mind here we are only this diffusion only occurs when the contaminant is in the aqueous phase, right? It can change, it can go from, let's say, what do you say, the water that's inside the solid to the leachate that's outside the solid through diffusion now. So obviously it should be dissolved now, right? So again, this compound can also be undergoing any other reactions leading to its loss, well, even formation, but that's relatively rare in this scenario. So but even if it's formation, you can write it accordingly by changing this particular sign, right? So let's say if the compound is being precipitated or such, that needs to be taken into account. So this is that, let's say for example precipitation is occurring, I am going to take into account the loss of that compound from that volume of water inside this particular pore space, let's say, by this rate of loss, and this gives me the loss due to diffusion or the diffusion term, right? And this obviously gives me how the concentration is changing with time, let's say, in this whole system of, and what's the system here? The water in the pore space, let's say, right? So again B, so how do I go about that? There are different models. So single component, So, I am assuming that the contaminant is the only component of concern here, right, and obviously I need to be able to assume some what do we say, boundary conditions to be able to solve that. So, what looking at this system, what are some of the boundary conditions? We are going to assume that it is an infinite bath, as in the concentration outside this particular what do we say, system, let us say outside the system is 0, right. So, it is an infinite bath, right, as in the concentration in this region is 0, right, and that it is an infinite solid, right. Now, what does that mean? That the concentration within the solid, let us say, is always the same and is always at a certain particular value now. So, that that is a decent enough assumption, especially assuming that you have considerable what do we say, quantity out there, and the loss is due to diffusion now, let us say, right. So, what are the boundary conditions we are looking at? That outside this particular mass that you are referring to, or the control volume, let us say, you are assuming that it is an infinite bath, right, or infinite dilution. So, the concentration is 0 outside the system, and inside it is an infinite solid, right. So, even though diffusion is taking place, the concentration of that relevant what do we say, compound or such is more or less at C naught or such, right. So, we are going to assume that, and also assuming that there are no other reactions occurring. So, we are assuming that no other reactions are occurring. So, what does that mean? That means that rate of loss is equal to 0, right. So, from that I am going to end up with dC by dt, or d equal to diffusion coefficient, second derivative with respect to x, right. And to solve this, we will more or less get C as a function of x, right. So, that is what you see here, right, or C at time t is a function of x. So, I have the solution, I believe, here in the next slide. So, looks like if we solve that, we get that concentration at x comma t is C naught error function of x by square root of 4 det. So, again transforming that into variables that we need, which is mass that has leached out by the initial mass is equal to the square root of 4 det by pi L square, right. 4 diffusion coefficient, time, let us say, pi, and L is typically the length, let us say, that is perpendicular to your, or in the direction of diffusion, let us say, right. So, that is one aspect to look at, and if it's spherical or such, we look at total volume by total surface area and so on. So, different ways, but we will look at that in greater detail. So, this is what we have out here, right. So, let us try to see how that happens. So, something like this, let us say, right, the mass that is leached out, right, as time keeps increasing, let us say, right. So, here we have mt by m naught, and with time, as you see, the profile more or less flattens out. So, why is that? Obviously, it is because, let us say, over time, right, what happens now, the concentration gradient decreases, right. Again, what drives diffusion? That we have a region where the concentration is relatively higher, and one region where concentration is relatively lower, and the system wants to see to it that this is where the system finally ends up at, right. But obviously, at this stage, the relevant transport is relatively greater, let us say, and as we move to this particular state, obviously, right, the concentration gradient is less. So, that is why you see, let us say, its effect on the relevant diffusion here, because the concentration is relatively less as you progress along with time, even though our assumptions were infinite solid, right, and that is something that obviously happens out there. So, again this is something to keep in mind, right. So, part B is when let us say we have sorption or desorption, let us say, right. So, sorption or desorption to be taken into account. For example, in the earlier case, we assumed that no other reactions were occurring and so on, or there was no adsorption, desorption, or precipitation and so on. So, we are not going to look at the case where we have precipitation or the compound being removed from that what we say, water in the pore space by being precipitated out, but we are going to look at, let us say, adsorption or desorption and the relevant effects. And this is something we did look at earlier, but let us just write that down. dC by dt is equal to, again, the diffusion coefficient or dispersion coefficient, let us say, and second derivative, let us say, right, of concentration, right, minus rho by the porosity, bulk density by porosity, pardon me, and dq by dt, right. What is this Q? Q is nothing but the concentration of contaminant per not concentration, pardon me, mass of contaminant per mass of that media, let us say, right, or it gives you an idea about the concentration of the contaminant adsorbed onto the media, right. So, its Q will obviously be depend upon concentration in the aqueous phase, right. For example, let us say we know that let us say you have a solid here and a compound can either be in the aqueous phase or it can be adsorbed onto the solid. Now, how is it going to be depend upon? Let us say it obviously is going to be depend upon the number of molecules or the concentration in the aqueous phase. So, the greater the number typically in this aqueous phase, so the greater the concentration in your or on the solid now. So, Q is equal to Kpc if we assume that it is a linear relationship, right. So, I can plug this in here, and this is something we looked at with respect to, I believe, mass transport or natural attenuation and so on and so forth, right. So, I can plug this in here, Kp times dC by dt, and why is this negative here? Why is this negative here? Because Q, right, what is Q? Q is the mass of the contaminant per mass of that media. Q increasing, what does that mean? If Q increases, C will decrease. What is C? C is the concentration in the water, right, or in the water in the pore space. Q is the concentration in the or on the solid now. So, if concentration on solid is increasing, what will happen to the concentration of the relevant molecule in the water? It will obviously decrease, because where is the mass of the contaminant coming from? Only from the water, it is going into the or onto the solid now, right. So, if Q is decreasing, what happens? It means that the compound is being desorbed. So, the contaminant is being is changing from being adsorbed and moving into the aqueous phase, right. So, that is why let us say dC by dt will have the opposite sign as dQ by dt, right. So, plugging this in and so on and so forth, let us see what we have. So, we have dC by dt, and taking this term out to the left, again we do not need to mug stuff up, but we need to understand, let us say where we are coming from, let us say, right, is equal to second derivative, and this obviously, if you remember, that is the retardation coefficient, right. And now maybe it seems familiar to the case when we looked at the case for natural attenuation and looked at trying to model the relevant scenario, right. So, now I am left with dC by dt equal to d observed. D observed is obviously dE by R by, yes. So, again this is similar to what we already had earlier here, right, but instead of d effective diffusion coefficient or dispersion coefficient, we have the d observed, right. So, again the relevant solution will be similar, and we will end up with mt by m naught is equal to square root of, let us look at what we have here, pi L square here 4 d observed now into time, I believe, right, okay. So, that is what we see here, right. So, this is the equation obviously, but let us try to understand this now. So, what is the effect of having adsorption here, right. In the earlier case here, we assume that it was only diffusion out, but if we are also considering that the compound can be adsorbed onto the relevant media or the solidified and stabilized mass, so what can happen now, right, think of that. So, as in what is happening to d here, or this term compared to what we had earlier, it is now dE by R, or it is decreasing. So, if this decreasing, what happens to mt by m naught now? It means that mt by m naught is also decreasing. So, that means that the effect of what do we say adsorption obviously decreases the mass that can leach out, right. Obviously, it makes sense, again thinking about it logically, and even if you look at in the equation. If we had no what do we say adsorption, pardon me, it would not have been the d absorbed, but just the d effective diffusion coefficient. But now as we see, we need to divide that by R, meaning that d observed is going to be smaller than dE, or effective diffusion coefficient. What does that mean, or what is the effect that we can visualize from this equation? That means that mt by m naught is smaller. Mt by m naught is smaller. What does that mean? That the mass leached out at certain time is lesser than the case when there is no adsorption, right. So that's something to keep in mind now, right. So until now we have looked at single component models, right. So then we can also have multi-component models, as in other than just looking at the contaminant, we can also have to look at the effect of pH, effect of alkalinity, and so on and so forth, right. So we can have the relevant theoretical models, right, but typically making the actual measurements when we are looking at multi-component models and such is more worthwhile way to go about the relevant aspects, right. So now let's move on to how to get things done now. Let's say we understood what happens and so on and so forth, but let's say now I want to solidify and stabilize a certain waste. What are the aspects that I need to consider? I need to know how much waste, how much cement, how much fly ash, and how much water I need to put in. But what's my objective here? The objective is that I want to see to it that it cannot be classified or should not be classified as a hazardous waste, or that it minimizes the leaching, right. So two ways. What are they? One, that it minimizes the actual harmful effects, right, say such that the leaching is minimum, or such that if and when the relevant authority or you, let's say, conduct the TCLP test, right, it shows up that the relevant contaminants in the leachate are relatively less than the thresholds, right, or after solidification and stabilization this waste is no more a hazardous waste. So there are two approaches, right. So two approaches here. What are they? We will discuss the first one. The first one is the TCLP approach, right. It's the TCLP approach now. So what's this about? So you, let's say initially you have your waste, let's say the Moradabad site, and you have the relevant waste, and you conducted the TCLP test, and you saw that in your leachate, let's say, or in the TCLP test leachate, you saw that the contaminant concentrations of or the concentrations of various heavy metals were very high, and thus you had to classify that as hazardous waste, and thus accordingly need to dispose that. But now let's say after you chose solidification and stabilization, so you solidified and stabilized that particular waste now, let's see. Even after that, obviously you need to conduct the TCLP test to check its effectiveness, let's see. So after conducting the TCLP test, again we are going to on this solidified and stabilized mass. How are we going to do that? We are going to first break down the solidified and stabilized mass to less than 9 mm size, if I am not wrong, right, 9 mm size particles. Then look at the relevant what do we say extraction fluid that needs to be added depending on the pH, and then we are going to add the acetic acid, right. We are going to add the acetic acid to bring down the pH to a certain value, and then let it equilibrate as an end over end mixing for 24 hours. So what is the assumption here? That as I decrease the pH, let's say, the relevant contaminants will leach out into the leachate, right, or will leach out into the relevant solution, let's see. But when I am looking at the TCLP approach, what am I going to do? I am going to maintain the pH to be high enough that even after addition of this acetic acid, the pH is going to be at the optimum value, right, so that the heavy metals do not leach out into the relevant solution. Makes sense, hopefully. Let's try to understand that. It's like beating the test now, as in you are writing the test, let's say, to only pass the test, not to learn the relevant aspects, let's say. That's going to be relatively different to what the second approach. But here what's the approach now? Your approach is to just beat the TCLP test. So if you conduct the test on the solidified and stabilized matrix, it's going to show that it's not a hazardous or can't be classified as a hazardous waste. So what are the aspects, obviously, that we need to keep in mind, or how do we go about it here, right? So let's look at the relevant aspects now. So what do I need? Obviously I need amount of cement, fly ash if I am going to add that, water, and waste, right? So we have to find these what do we say, fractions, right? So what's the approach here? Again, we are trying to beat the TCLP. So to beat the TCLP, what do we need to look at? We need to find the optimum pH, right? The optimum pH. And how do we find this optimum pH? Obviously, right, we are going to find the optimum pH such that even after addition of your extraction fluid or the acetic acid in your TCLP test, the pH will be high enough such that the relevant heavy metals will not leach out, right? For example, we know that for lead, PbOH twice solid, it will dissolve into or be in equilibrium with Pb2 plus and 2OH minus, right. So, this is what we have. So, let us say in the TCLP test we are adding the acid, right. What does that mean? We are decreasing OH minus. As this decreases, the system moves towards the right, as in your PbOH twice this solid is going to dissolve now, right, and now you are going to have higher concentrations of Pb2 plus in your leachate, let us say. But to see to it that the Pb2 plus concentrations do not cross a certain threshold, what do you need to do? You will see to it that your OH minus initially, or the initial pH is high enough that even after decreasing the OH minus or adding the acid, right, you are going to see to it that this Pb2 plus final concentration will not be, higher than the relevant threshold. So, that is what we are saying when we are looking at pH or optimum pH, right. We will look at that approach or calculations, pardon me, and obviously in this case I need to choose binders. So, binders again typically cement, fly ash, there are other binders too, and again binders can have, or can increase the pH, or some of them can even decrease the pH, right. So, we need to look at these aspects again, right, and that is something we will take into account. So, again how are you going to add the binders? You are going to, so let us say some of them can increase the pH, some of them can decrease the pH. So, you will need to look at the fractions in such a way that you end up with the optimum pH, right. So, again keep in mind that let us say as we looked at it for lead, let us say, right, if this is the pH and this is the total dissolved concentration, let us say total dissolved concentration, we saw that the profile is something like this for lead anyway, but for maybe chromium it can be something else, right. So, what I am trying to say is that there is no one particular optimum pH at which let us say all your particular heavy metals are going to be precipitated out or such, let us say, or stay in the solid phase. So, what do you do now? So, depending upon let us say cost considerations, let us say, and relevant aspects, you are going to choose a range, let us say, or one particular optimum pH. You are obviously not going to have one particular pH, but you can choose the optimum one. And also to increase the range, let us say, where this pH is optimum, let us say, you can also add some admixtures, for example like phosphate, let us say, PO4 3 minus, let us say. This what we say again, I believe complexes, not complexes, precipitates out, or precipitates out, precipitates lead out, pardon me, right. And thus let us say it is not just OH minus you are dependent upon, but obviously PO4 3 minus concentration, and that increases the optimum range, let us say. Similarly, it can precipitate out some of the other heavy metals, or you can add iron, let us say Fe2 plus, let us say, that can reduce chromium from oxidation state 6 to oxidation state 3, and you know that oxidation state 6 is very highly soluble, or it mostly wants to stay in the aqueous phase or dissolved in water, but once you use ferrous iron, let us say, to degrade chromium 6 to chromium 3, as in these can be added as the admixtures, so let us say, right, admixtures, right. And you know that chromium 3 is very less soluble or insoluble, and that is going to precipitate out as CrOH thrice solid, right. Again it is relatively more insoluble compared to chromium 6. So, there are different ways to work things out, right. So, now let us move on to calculations. As in we looked at the relevant aspects, how do I go about getting the relevant fractions and so on and so forth, right. So, let us look at how we get that done now. Obviously, the whole key is we want to maintain the optimum pH, right, and the optimum pH is such that even after addition of your extraction fluid or the acetic acid, you are going to have the pH to be high enough such that the metals do not dissolve into the relevant solution now, right. So, what is the key here? We know that let us say we know if you look at the TCLP test, we know that we add 20 ml per 1 gram of the waste, right, and extraction fluid, if you calculate the relevant aspects and so on, let us say, let us see what it comes out to. We have 20 ml into 0.1 milli equivalents per ml, let us say, right. So, that as you can see will be equal to, and this is for extraction fluid 2, extraction fluid 2, this is the acid neutralizing capacity, not acid neutralizing capacity, the amount of acid, let us say, right, milli equivalents of acid that you are adding per ml, let us say, right. So, what is that equal to? You see that it is equal to 2 equivalents, right, or 2 milli equivalents, right. So, 20 ml into 0.1 milliequivalent per ml. So again, what is this? More or less the amount of H plus that we are putting in, right? It's the equivalents. We are expressing it in terms of equivalents here. So I'm adding 20 ml of extraction fluid per gram, right? So per gram, how many equivalents of acid am I adding? It's 2 milliequivalents of acid per gram, right? So that's what I'm adding out here, right? So this is from the extraction fluid 2. You can look at the relevant calculations here. So what is it now? What am I trying to say? That we are putting in acid at rate of, not at rate, at the amount of 2 milliequivalents per gram of your waste, right? So what characteristics does your acid need to have now? So not the acid, pardon me, the waste need to have. The waste needs to have an acid neutralizing capacity. And how much acid neutralizing capacity should your waste have? It should have 2 milliequivalents per gram of your waste, acid neutralizing capacity. So we are now going to look at the term acid neutralizing capacity. Right, so we are going to look at acid neutralizing capacity. So I believe you might have or you would probably know or have heard of alkalinity, right? Alkalinity typically, the theoretical equation anyway, or definition anyway, looks at the amount of hydroxide, H plus, CO3 2 minus and HCO3 minus. Again, what are these? More or less bases, right? OH minus, HCO3 minus and CO3 2 minus, they are bases. So in effect, we are trying to calculate the acid neutralizing capacity of a particular solution when we say alkalinity now. How do we measure alkalinity now? You take a relevant solution and you take an acid and you titrate it until you reach a particular pH, typically 4.3 or 4.5, when you neutralize all the HCO3 minus 2, right? But if people not HCO3, yeah, all the HCO3 minus, but if people want to look at a different endpoint, some people choose 7. But again, let's not go into that in that detail. Typically, we look at 4.5 or 4.3 as an endpoint. Why is that? We want to see, let's say, how much acid that the solution can consume, let's say, right, before reaching to 4.5. So that, as you can see, is the acid neutralizing capacity. But in your case or in our case, what should it be now? It should be such that, or we will look at it such that, what's the acid neutralizing capacity for our optimum pH, right? So you are going to choose the design pH to be your optimum pH, right? Your optimum pH, right? The design pH will be your optimum pH that you are going to calculate from your relevant heavy metal based, precipitation based data, which we are going to look at again, right? And you are going to look at that, we are going to try to maintain that pH. So if I have a graph as in pH versus the acid neutralizing capacity, let's say, I'll choose that acid neutralizing capacity for that particular pH, let's say. For example, this is my graph, let's say, just assume that. So I'll have to choose this acid neutralizing capacity, right? So but the key here is that fly ash has its own acid neutralizing capacity. Water, let's say, might have some of its own acid neutralizing capacity. Cement certainly will have, because again, cement is relatively higher pH, right? And what else now? I think the waste itself, right? So you have different aspects that are taken into account. So but the total acid neutralizing capacity should end up being 2 milliequivalents per gram. And how am I going to get that? It's going to be the fraction of water into acid neutralizing capacity of water plus fraction of cement into acid neutralizing capacity of cement plus fraction of fly ash into acid neutralizing capacity of fly ash plus fraction of waste into acid neutralizing capacity of waste, right? Again, we have an equation here, but what is it that we are expressing? So this is the relevant mixture, right? After solidification and stabilization, these are the different components in the mixture, and we know that this mixture will be facing or exposed to certain acid. How much acid? We know that it will be, the acid will be at 2 milliequivalents per gram, right? But you want to see to it that the pH does not fall below a certain pH, right? So what do I need to do? I need to change these fractions, right, such that the total acid neutralizing capacity will be 2 milliequivalents per gram at that particular pH, right? So that's something to keep in mind and take that forward, right? So obviously, what are the other equations that I have? That's one equation. Typically, I will be having a water by cement ratio, that's something I will have, or water by fly ash ratio, right? These are equations that we typically need to maintain for different reasons such as structural integrity. And obviously another equation is that all the fractions obviously need to be equal to sum of fractions needs to be equal to 1, right. It is fractions, so sum of all the fractions obviously needs to be equal to 1. So, I guess we are again running out of time, so I will end today's session, and then we will continue this discussion in the next class, I guess, right. And that is it from me for today, and thank you.